Let's look at some further examples of using the binomial theorem to expand binomials. So in this example, we have x squared plus 2y all to the power of 3. So in this case, our a is x squared, our b is 2y, and our n is 3. So using the binomial theorem then, we have the following. So this equals to n choose 0, so in this case 3 choose 0, multiplied by a to the power of n, which in this case is x squared, all to the power of 3, since our n is 3, multiplied by b to the power of 0, so in this case 2y all to the power of 0. Then for the next term we have n choose 1, so in this case 3 choose 1, multiplied by x squared to the power of 2, since n minus 1 in our case is 3 minus 1, which is 2, so that's x squared all to the power of 2, multiplied by 2y to the power of 1, since we have b to the power of 1 and our b is 2y. For the next term we have 3 choose 2, multiplied by x squared to the power of 1, multiplied by 2y to the power of 2, and then our final term is 3 choose 3, multiplied by x squared to the power of 0, and then we're finally multiplying by 2y all to the power of 3. If we now simplify this, we get the following. So 3 choose 0 is equal to 1, using either the formula or using a calculator. X squared all to the power of 3 is equal to x to the power of 6, since we multiply the powers when we have brackets here, and then 2y all to the power of 0 is equal to 1. Then for the next term we have 3 choose 1, which is equal to 3, x squared all to the power of 2, which is equal to x to the power of 4, and then we have 2y to the power of 1, which is just 2y. For the next term we have 3 choose 2, which in this case is equal to 3, and then x squared to the power of 1, which is equal to x squared, and 2y all to the power of 2, which is equal to 4y squared. Then for the next term 3 choose 3, which equals to 1, and then we have x squared to the power of 0, which is equal to 1, and then 2y to the power of 3, so this all becomes 8y cubed. If we now simplify this further, we have 1 times x to the power of 6 times 1, which is x to the power of 6. For our next term we have 3 times 2, which is 6, times x to the power of 4 times y, which gives us 6 x to the power of 4y. For our next term we have 3 times 4, which is 12, times x squared times y squared, so this gives us 12 x squared y squared. For the next term we end up with 1 times 1 times 8 y to the power of 3, which is equal to 8 y to the power of 3. And so x squared plus 2y all to the power of 3 equals to this when expanded out. This next question says, what has been expanded to give 32x to the power of 5 plus 80x to the power of 4y plus 80x cubed y squared plus 40x squared y cubed plus 10xy to the power of 4 plus y to the power of 5. So we see that our first term is 32x to the power of 5. And so in the binomial theorem, for the expansion of a plus b to the power of n, our first term is n choose 0, a to the power of n, b to the power of 0. So essentially what we're trying to do is we're comparing the first term in this expression here with the first term in the binomial theorem. So what we can do is we can make an equation. So n choose 0 multiplied by a to the power of n multiplied by b to the power of 0 equals to the first term here, since the first term in our expression is going to be equal to the first term in the binomial expansion for the binomial theorem. We know that n choose 0 is equal to 1 using our formula here, and b to the power of 0 is also equal to 1. And so in this case, on the left hand side, we're left with a to the power of n, which equals to the right hand side, which is 32 x to the power of 5. And so we have a base here of a and a power of n. And so what we should do on the right hand side is try and rewrite this so that we end up with a single base and a single power. So in this case, 32 can be rewritten as 2 to the power of 5. And so we have a to the power of n equals to 2 to the power of 5 multiplied by x to the power of 5. Since we have the same powers here, we can rewrite the right hand side as the following. So a to the power of n equals 2. So combining these two, 2x all to the power of 5. If we were to expand this out, we would end up with 2 to the power of 5 x to the power of 5, which would equal to 32 x to the power of 5. So we're just working backwards now to write a single base and a single power. And so comparing the left hand side with the right hand side, then we have the following. So our base here, a, should equal to the base on the right hand side, 2x. So a equals to 2x. And comparing the powers, n must equal to 5. And so what we have already is, in our bracket a plus b all to the power of n, we now know what a is equal to, which is 2x, and we know what n is equal to, which is 5. Now to finally work out b, we can look at the last term in this expression, which is y to the power of 5, and compare this with the last term in the binomial theorem, which is n choose n, a to the power of 0, b to the power of n. So again, making an equation, we have y to the power of 5, which should be the same as n choose n multiplied by a to the power of 0 multiplied by b to the power of n. Again, n choose n, if we were to use the formula here, we would end up with 1, and a to the power of 0 is also equal to 1. So we end up with y to the power of 5 equals to b to the power of n. And so comparing the bases, if the base here is b and the base here is y, then these two must be the same for y to the power of 5 to equal to b to the power of n. So we have that b equals to y, and then the powers must also be the same, and so in this case n must equal to 5, which we already established from the previous bit here. So now that we know what a, b and n are, we can finally write our bracket, which when we expand gives us this expression here. So if we were to rewrite this as a single binomial, we would get 2x plus y all to the power of 5. And so if we expand this out using the binomial theorem, we end up with this expression here.